really just interpreting those overall mechanisms, which is why we spent a lot of time looking at the mechanisms. After that, I've noticed the tutoring center does this as well. You can go through and you can summarize the crap out of substitution, and you can summarize it for elimination, come up with all the text and the words to be able to say, oh, this is what happens here, this is what happens here. Ultimately, what you have to do is practice, right? Because you will not be seeing text on the exam. You will be seeing structures. So you could go through and get everybody's help in the world on organizing, oh, if you have a tertiary alkyl halide, then it's SN1, or it's E1, or it's E2. Okay? But until you actually see and work with those structures, it's not going to help out. Okay? So, along those lines, where I ended that online recording was looking at a whole bunch of practice problems. And with these ones, I actually said, assume that it's an SN1 reaction. Go through and predict what your products would be out of each of these. Okay? Theoretically, you all did this. Okay? Some yeses and some nos. So let's go ahead and spend some time working on these four. Then we'll shift to these four. And then we'll open it up for any questions that you guys might have. I am still working on the exam, unfortunately. I thought I was a lot further than I actually was. So that might be contributing to the headache. So if you've got questions, talk to the people. So we were told to assume SN1, which, as a few of you pointed out, is that a good assumption? No, it's a pretty horrible assumption. Okay, so let's address that assumption first. And that first reaction, why is it horrible to assume that first reaction is SN1? So I'm hearing some primary carbocation discussion get tossed out there. That is absolutely not why SN1 is bad. The SN1 is actually okay here, and it's not primary carbocation. Okay, so let's address the primary issue. Take a look at our nucleophile. Our nucleophile is, how do you know it's strong? Because it's negatively charged. As soon as you see the word strong, you should immediately be thinking number 2. Okay, period. Okay. Substitution versus elimination. We'll address that a little bit later, but all we're looking at here is substitution. So if we've got strong, it should be an SN2, not SN1. Okay? So if we ignore that and say we are running under the SN1 conditions, I heard a couple people shout out that you've got this issue with a a primary carbocation. So to see that, what would have to happen is our leaving group needs to leave, and we would end up with the result shown here. And while you may all be shouting at me that that is a primary carbocation because it is connected to only one other carbon, it is not just a primary carbocation. It's an allylic primary carbocation. Allylic primary carbocations are equivalent in stability to a tertiary. Okay? So primary, secondary, tertiary, we just looked at, are there electrons nearby? There was no electron pushing. We just said, oh, there's more electrons around the tertiary. That makes it more stable. Okay? In this case, what do we have? Yes, we have a primary, but is it just a primary? No, I have the option to physically move electrons to stabilize the carbocation. And the result I end up with is now a tertiary carbocation. I have a resonance contributor. That resonance immediately stabilizes the carbocation, more so than just primary, secondary, tertiary, and we now can see that carbocation form. So an SN1 mechanism is valid as far as the carbocation goes. Okay? Once we formed the carbocation, we now have to decide what the next step is. Before we do that, are you talking about earlier?
Do you have a positive charge on a carbocation on a double bond?
No, we cannot put positive charge on a double bond. Okay? So our positive charges will only exist on it's hard to call them sp3 atoms. Yeah, for lack of a better description, our positive charges can only be on what was formerly an sp3 atom. Okay. Why do we say formally? What's the hybridization of a carbocation? It's sp2, so can't quite call it like that. Okay. So once we've got our carbocation, we now have an issue, because our nucleophile can either come in and attack our primary or come in and attack the tertiary, potentially resulting in two different products. So which product is the correct one?
The first one.
Okay. The analysis that we've been using is looking at the stability of the carbocation. Okay. Our carbocation would suggest that we want the tertiary. Hate life. And that is our major product. Is it as simple as that? No. We'll address that complexity when we move to second semester.
Does it matter where you put the CN attaching to it? Like if you're showing it from the bottom, does that matter if you were to show it coming from a different place? Or would that be the best place due to just what that structure is? That would be the easiest place for it to
So you,
attack?
let me check. Is what you're asking?
Yeah, basically.
Is that still equally valid?
Yeah.
Okay, well, you tell me.
Yeah, you can rotate that.
It's a tetrahedral structure that you can freely rotate. Okay. One issue that you may start to realize with this is that product has a very interesting condition. What is that interesting condition?
It's stereophore.
What is the? It's a chiral product. Right. Why did we not specify wedges and dashes on this?
Because they're all
Did we start with anything? So do we know if it's wedged or dashed? No. So we don't need to specify it. We can just imply it by just showing the 4 standard bonds. As soon as we put in wedges and dashes, we're now specifying we have one product. Right? So if we want to get more specific with this, we could go through and say that this is our product plus, and in this case we could get away with it, an enantiomer. We don't need to bring that in, primarily because we didn't start with chirality. Okay, so it's one of the things we can kind of dodge that point on. Question? Yeah.
Can you clarify again why it is that we get the react before we get the product in the box there? And because you said a primary carbocation, a little primary carbocation is just as stable as a tertiary carbocation.
Is just as stable as a tertiary carbocation. Absolutely right. But is a primary, or sorry, an allylic primary carbocation just as stable as a tertiary allylic carbocation? No. So our tertiary allylic has slightly more stability than the primary allylic, okay, for the same reason that a tertiary is more stable than a primary.
So that would be the intermediate form.
That would be our intermediate, yep. Other questions? Okay. Since everybody skipped it, we'll skip that second one for the moment.
Okay.
What's that? Darn? No? Okay. Is it on the board?
There's two. There's two.
Oh, you're talking about that.
No, the second one I don't see on the board.
Two going straight down.
Okay, so we'll call this number 2 for the moment. Okay. What's the result? I noticed a lot of people saying strong base, so immediately say strong base elimination. Hold your horses. Before you do strong base elimination, what do you need? You still need a leaving group. Okay, so we do have a polar bond there. So we go, oh, well, there's our leaving group, except that leaves as OH minus, which is a bad leaving group. Take it a step further. Let's assume that that reaction did occur. Actually, no, we can't quite do that because that gets me something else. We would end up with a triple bond within the ring, which starts to get a bit dicey too. okay, if we try to do that elimination. Not that it can't be done, but it's not done with these reagents. Okay? So, before you start immediately jumping to elimination when you see a base, remember, a base primarily acts as an acid. Even when we do the elimination reaction, what is our base doing? Still acting as a base, accepting a hydrogen. So we have to find an acidic hydrogen. Is a hydrogen connected to a carbon particularly acidic? No. Okay? If that is the only choice, as it is with most of our elimination reactions, what does the base react with? It will react with that hydrogen. Is that the most acidic hydrogen in this structure? The hydrogen attached to the oxygen is much more acidic. Why? Oxygen is more electronegative than the carbon, meaning it's already taking those electrons away. So when you look at a reaction, don't just start jumping into each of these mechanisms. Look at it, evaluate its reactivity, and say, okay, it needs to act as a base. I need an acid. If the most acidic thing happens to be a hydrogen connected to a carbon, yeah, an elimination makes sense. That's not the most acidic thing in this case. The most acidic thing is that hydrogen attached to our oxygen, which means if we looked at our curved arrows, our electrons come across, pick up the hydrogen, and we now end up with that negatively charged phenoxide structure. Right? We got something kind of new introduced here. You'll notice that we've got this labeled as 1 and 2. What is that supposed to represent? There are 2 steps, 2 reagent steps. We react 1 first. The end result of 1 is that phenoxide structure. What happens then? Well, I'm done with step 1. What should I do? Move into step 2. So we again go through and compare. I have a negatively charged oxygen, just like I had here. A negatively charged oxygen could very well be a strong base. Okay? Again, should we be looking at base? Why? You're told at the outright that it's substitution. So what happens? Oh wow, this one's really ugly. We'd have to have our leaving group leave first, have the nucleophile attack, and what we'd end up with is that final product. Does it make sense for it to run as an SN1 mechanism? Why not? In an SN1 mechanism, what has to happen? The leaving group must leave first. If it leaves first, what kind of carbocation do we have? Is it primary allylic? No, it is straight up primary. Do we expect to ever form primary carbocation? No. Okay? So again, poor example for the SN1 mechanism. Last one. Or actually, before we do that, questions? Yeah.
Could you say that that portion of the mechanism would be considered an SN2 reaction? And then the overall reaction would be
So let's break it down. What type of reaction happened in that first step? It's not substitution. Look at what changed. The only thing that changed was the location of a hydrogen ion. That's an acid-base reaction. There is nothing more complex than that. It is strictly acid-base. What happened in the second step? It's a substitution. If we tried to push the mechanism, we'd really say that's SN2, not SN1. Strong nucleophile and primary substrate.
I guess that's where it was confusing me, because it technically is still 2 steps, but one's an acid base, one's an acid.
There are different meanings to steps. There are 2 mechanistic steps. So in 2 mechanistic steps, I am doing 1 reaction that requires 2 steps, 2 drawing steps. There's then the situation of 2 reactions. 2 reactions, each of those reactions could involve several mechanistic steps. So there's a big difference between a reaction step and a mechanism step.
So those are reaction steps.
These are reaction steps, not mechanistic steps.
And so with assuming that SN1, you're assuming the second reaction step is the SN1 portion?
We're told to assume SN1. In this case, the best we could do would be, if it's really SN1, that it wouldn't happen. Okay? If we're told that we have to draw a product, that's the product we would show. Last one. Last one's actually okay. We could get away with showing or stating this one's SN1. We have a secondary substrate. We do have a reasonable nucleophile, but that nucleophile could work for both SN1 and SN2. And you'll notice that what we've got drawn up here are two products. Well, which one's the product? Why both of them? If we go through and form according to the SN1 mechanism, the very first step of our mechanism is the leaving group leaving, which then results in the secondary carbocation. That secondary carbocation can be attacked either from the top or from the bottom of the structure, giving us both possible products. So on an exam, you would be expected to make sure that both of those were in your answer. How could you do that on a multiple choice exam? Okay, one of your answers would be both A and B, okay, or something like that. Okay, I'm about to run out of here again. So, last question on there. We did not actually have to make the statement that we should assume SN1. Okay, how do we know this reaction is SN1? There are two products, and those products are enantiomers of each other. Okay, so we know we're doing an SN1 mechanism. Okay. For us to do an SN1 mechanism, we have to have a good leaving group. Fine. Okay, what else do we have to have? We have to have some kind of nucleophile. So what would be our nucleophile that we could react it with? There are two carbons, right? Okay, and I heard someone suggest S minus. What's the problem with S minus? It's a strong nucleophile, which would SN2. And if we ran SN2 mechanisms, would we have two products? No. So we're right that we need the sulfur and we need those two carbons. We're wrong in that it cannot be negatively charged. So how do I fix that? Can't just erase the charge. Not a bad idea, but not quite. I need to attach something to it that can be easily removed, say like hydrogen. You now have a weak nucleophile that would facilitate the SN1 mechanism. Okay? So if we went backwards and looked at these slides, once we've made the assumption that we are looking at one of those mechanisms, we have to make sure that all the rules follow accordingly. And if they don't follow, then we can't use them. Okay? Okay. Here's another set. I'm usually better at SN2, so I think all of these, yeah. I'm going to change it. Here we go. What's product now? Yeah, you should all know what the delta means. Delta means heat. So if we're now adding heat, why is that problematic?
It's not an elimination.
Nothing to do with the hydride shift.
It's an elimination.
We're going to be doing an elimination mechanism, not a substitution. Right. So with that heat, we would expect our elimination product, and the product we would get would be either 3 or 4.
3.
And the answer comes out as 3 because more substituted double bonds. Okay? So that's the Zaitsev product, if you remember that. If I wanted 4 as an answer, how do I get 4 to be an answer?
Get a
The base that I need needs to be bulky. What's a good bulky base?
something.
T-butoxide,
Yeah.
which very rarely do you ever see drawn out like I just drew it out there. more often than not, it's drawn out as O minus C cH3 Okay, just be aware of that. That is your bulky base. Why would that happen? It's now a bulky base. It's going to react to the most available hydrogen, the easiest to get access to. That's usually the terminal one, the least sterically hindered. Okay. Questions on those, making those elimination?
You said it's going to react with the most available hydrogen?
Yeah, in an elimination, yeah.
No.
So now let's switch it back to our substitution, SN2. What's the product we expect? Should expect 1. How would I get 2 as an answer? If I somehow change the conditions to make it SN1. Okay. So if we go through and actually walk through these, we've got our SN2 product. We have our SN1. This could be E1 or E2. This last one could only be formed through an E2 elimination. Okay? Is that pencil in your forehead hurt?
Yeah.
Yeah. Just checking.
It's a little disappointing.
Questions on that? Can anybody see how these questions can get very quickly easy to lose track of? Pretty much every answer you're going to see can be formed through some form of mechanism, but you're looking at slight changes to the overall reaction conditions to push one over the other. Okay, so you have to be careful with evaluating each of those pieces. Got a lot of people super excited to see this one. Got a lot of people giving me this answer.
No.
That becomes problematic because that nucleophile is now weak, which pushes SN1, and I would expect 2 products. I only want 1 product. It needs to be the strong nucleophile. Make sense? Let's skip that big alkyl halide one for the moment because people had more questions on that one. For the last one, what product do we expect? Why the dash CL? We're doing backside attack because this is under SN2 conditions. We cannot form the other product. Okay, so we only get 1 product with that inversion of stereochemistry. Okay. Which takes us back to the alkyl halide. These are fair questions to ask, which are actually kind of fun. Okay. What you're trying to do is now look between the information you're given and see what stuff is missing or what stuff needs to show up. Okay. This is actually kind of nice because we know that what we see in the product had to have come from the reactant. And if all I'm given is CN triple bond, what I need to do is say, where is that in the product? It's right there. Which means what needs to show up in the box? Everything else. Right. For this reaction to work, what partial charge needs to be coming in on that carbon? It needs to be partially positive because it needs to react with that negative carbon of our nitrile. How can I make that carbon positive? I want to attach something to it that would take electrons away from it. What thing might take electrons away from that carbon? Anything electronegative. Why do we suggest bromine? As a hint, we were told you to say it was a halide, so any one of our halogens could have worked, okay, except for fluoride. So we could go ahead and put that bromine on there, which brings up our next issue. Okay, we have a stereocenter here, and we have stereochemistry in the product, which means we have to be very careful with what stereochemistry we assign to that bromine. Okay. Best way for me to describe this is guess. I'm going to guess it has to be wedged. I mean, after all, I've got a wedge in the product. It might as well be a wedge in the starting material. Okay. The next part of this is what makes this trickier. Run the reaction. You've got now, the entire thing is laid out in front of you. Just do it. See what happens. But in the process of just doing it, you need to make sure that you do not look at your product. Because now you are predicting what that product is. And if we go through and do that reaction, what's the net result? We would expect a dash for our carbon-nitrogen triple bond. Well, now that we've got that product, we can compare that to what we were asked to make, and it doesn't match. Okay, so what do we have to do? I have no idea why it's floating that weird thing there. Can I erase that? Whoa. What the heck is going on here? Hopefully it'll come back to me here in a second. For our starting material, we need to use that. All right. Questions? Kind of understanding the pieces? Okay, there's some shaking your heads and no. What are you missing?
Oh, we're talking about
Okay, that's fine. Other questions? Okay, we officially have 15 kind of free minutes. In theory, you have all already completed the practice exam, right? Everybody 100% done with it. Probably a good idea to get that finished immediately so that you can actually study. Okay, if you were doing that either tomorrow night, in fact, that's really your only choice. If you do it tomorrow night or day, you have now no way to study and review that material. So that needs to get done as quickly as possible so that you can then review the parts that you're missing and what you need to fix to advance forward. The exam is currently roughly 10 questions per chapter. But I've been doing too many different exams, so I don't remember our chapters. We've got 9, 8, 7, 6, right? So it's roughly 10 questions per chapter. I did notice, if I remember correctly, 9 and 8 seem to be sitting at 8 questions. And then 6, I think, has more. I think it's sitting at 14 or 15 questions right now. Okay. So I went through and put together all the questions that I liked into one big file, and that came out to be something like 60 questions, which I thought was a lot closer to 40, which is why this morning sucked, because I ended up going through and deleting questions. We should be sitting about 40 to 45 questions for the final, or for this exam, because that reflects what you see for the final. Okay, same question to time frame. There are some short answer questions on it. I do try and split up the short answer points so that if you know certain aspects of it, you can still get partial credit. Okay? There will be spectroscopy, just like in the practice exam. The practice exam has a brief spectroscopy question that will absolutely show up on this exam.
Short answer?
Short answer. Off the bat.
Because if you're doing SN1 or SN2.
I would argue we don't have to worry about between SN1 and SN2, yeah, we do kind of have to look at that. Do we have to stress as much about substitution versus elimination? Why not? Look at your product choices. Your product choices show no double bond. So we're not looking at elimination. So one of the things that I would immediately kind of narrow down on this, which I would recommend you guys do, is that you're then saying substitution, SN1 or SN2. Okay? That simple little note may seem like, oh, why do I need to bother with that? If you then skip this question and come back to it, you are restarting the question. If you've got this note, you've now already removed some of that time thought process. Okay? So you can get to your answer potentially faster. Okay? Continuing, what else do you see? So Danielle, you said poor leaving group. What's your poor leaving group? Okay. So what we're doing is evaluating sites of reactivity and seeing what could happen. So what you're saying is that OH is a bad leaving group. That would not happen on its own. So if that was going to be a possible option, if that's where my chemistry was going to lie, what would I expect to see as my reagent? What's that?
We are going to have an SN1
I don't quite want to go that far. If that's a poor leaving group and I want to make that a better leaving group, more than likely, what am I going to see over the arrow? Oh. Okay. What we've done, or what she's suggested here, is that OH is our substrate. Okay, that compound is the substrate in this reaction. Okay, because you have identified that that OH is a bad leaving group. If you are going to hold fast to the idea that that is the substrate, you need to have a good leaving group. What can we do to make that a good leaving group? Add a hydrogen, which means what do I need to see over the arrow? I need to see a proton donor, also known as an acid. So now I can look over the arrow and I see no acid. What should that tell you about your first assumption that that is your substrate? It is not the substrate. Okay? So with what I've got written, I might even then tag on not substrate, and I might panic and go, oh my gosh, this is weird. Why is not the substrate the first thing I'm looking at? Okay? But I now, when I come back to the question, I still have that information. I'm still doing what I would predict to be some kind of substitution, and I know that that OH structure cannot be the substrate. Okay? Well, if it's not the substrate, what is? The MEI. So this is a common question that I've heard a lot of people ask. What is MEL? Okay. If you can't understand what it's showing, or if you see some term that you're just like, what the heck is that supposed to mean? Raise your hand and ask. Okay. More than likely, I won't be able to answer. Okay. Under these circumstances, I absolutely would. Okay. But the information I would give you may not actually be all that helpful to you, depending on how much you've seen. That is not MEL, that is MEI, which means, what does MEI mean? It is not a metal iodide. Methyl. Did you guys say metal or methyl? Methyl. They're lying? I agree, they're lying. You guys actually said metal. So that is methyl. Good thing I don't have to take the test. I'm looking at methyl iodide. Why does that now change my perspective on this structure? Iodide is a fantastic leaving group, which means methyl iodide is very likely my substrate. Well, if it is the substrate, then what is the other species? It's going to be my nucleophile. What about it is going to be the nucleophile? Why the oxygen? Because there are implied lone pairs on that oxygen, making it an electron donor. Would I expect SN1 or SN2 under these conditions? It's actually kind of dicey either way you look at it. Why are we getting a mix of answers here? Those of you that said SN1, why do you say SN1? Octets are never destroyed in the course of an SN2 reaction. Okay. So that answer doesn't work for me. You start with a complete octet in an SN2, and you will end with a complete octet under SN2 conditions. And I could just as easily show this as an SN2 mechanism. The lone pair comes in, kicks out the iodide, one fell swoop, and I end up with a product. So
Then you have an extra.
we would think SN1 because it's a weak nucleophile. How do you know it's a weak nucleophile? No charge. Those of you saying SN2, why did you say SN2?
Because it doesn't give you two answers, like as an option.
No. Not a bad idea. That would only work if we had a chiral atom, and you'll notice in this one we won't have a chiral atom, so we don't have to worry about the stereochemistry issue popping up. And under SN2, we'd only get one product anyway. Why SN2? SN2 says strong nucleophile. So why were people suggesting that an SN2 was a valid mechanism? Every reaction that you look at for substitution elimination, there are 5 things you must evaluate. What are those 5 things?
Nucleophile, substrate, leaving group.
Nucleophile, oh, that was close enough. Substrate. Leaving group, which I'm actually going to put a line through. Yes, you should look at it, but it isn't that big of a deal. Solvent. That's 4. Base. Those are the 5 things you should evaluate. Do we need to be looking at base? Why not? Okay. It's not one of our possible answer choices. Bases would give us an elimination. Leaving group, do we have one? Yeah. Nothing about the leaving group is going to change what type of mechanism we got. Okay, so yes, leaving group's good. You said the nucleophile suggests that it is SN1. What else left is there to evaluate? The substrate and solvent. So evaluate one of those.
It's weak.
So we got a couple different answers coming out of here all at once, which is good. Solvent, there's none really specified. Unfortunately, sometimes if it's not specified, it is. It's the T-butanol. Okay, which is that methyl alcohol up there, or not the methyl alcohol, but the carbon alcohol, which would suggest it is what type of solvent? Protic, which leads us to SN1. Will, what were you suggesting about the substrate? If we ran under SN1 conditions, what type of carbocation would we have? Whoa, it's not even a primary. It's not a zero or not a tertiary either. Why is it not tertiary? Remember, identify where the substrate was. The substrate is here. Ah, go away, colors. The substrate is right there. And I heard primary, it's actually worse than that. It's zeroary. Why is it zeroary? There are no other carbons attached. Can we form a zeroary carbocation? No, which means SN2. So, what do we decide to do? SN1 or SN2? It's kind of a hard question to answer in that case. We're probably doing a mix of both because we cannot form a zeroary carbocation. Okay. Remember when we talked about mechanisms and we said, do we care which mechanism we have? Remember that conversation way long ago when we first started in chapter 9, chapter 8, chapter 9? Yeah, and it was absolutely because of chirality. Do we care?
No, because there's no chirality.
There's no chirality. Does the mechanism matter? No. Ultimately, our nucleophile is going to have to attack. We're going to have to kick out the leaving group. Either way we go about it, the product that we end up with which gives us answer B. Okay. So we did overanalyze that one because I want you to see all the possible aspects that are trying to go through your head.
I have a question.
Yes.
With what you have labeled as the nucleophile, if you took the OH and the bond between the OH, move those electrons to the oxygen, and have the oxygen plus the 3 metals as the leaving group, is that
We are actually done, so I'm going to try and answer your question afterwards. There is no good leaving group on what we have labeled as the nucleophile. None. At no point can anything in that structure take electrons nicely.